welcome to Advent of Code. Getting ready for the next day here. Let's see, we've got about 25 seconds left before the next problem becomes available. Our Advent calendar is filling up pretty nicely here. Yeah, that's the thing. No matter how many points you get or don't get, you still end up with the same Advent calendar in the end. So on that positive note, let's take a look at the problem for day 20. All right, GPU, too many particles. All right, a buffer listing each particle in order. All right, X, Y, and Z. Each tick, a particle's properties. All right, Z buffering. Which particle will stay closest to position using Manhattan distance? Okay. Okay, all right, I think I get it. So these particles are all going to be accelerating. Okay. All right, so we have some puzzle input here. Let's save this. It says input 20. Interesting. Okay. All right, I think I got it. So if we're to slurp in input 20 here, let's see. We want to split it up by lines. Let's see, maybe we can do something like this. Okay. Yeah, I think this will work. So if we have some parsing function here, taking in our, all right, so the thing, which particle will stay closest to position X, to this position in the long term? Okay. All right, so they have an acceleration and a velocity. All right. So, okay, I think I get it. So this is going to take P, V, and A here, and we need to decompose these. So I think for each of these things, we want to maybe do like an RE matches on some stuff, followed by this, followed by capture, comma, capture, comma, capture, and then that. Ending possibly with some stuff on like say P. All right, something like this. Okay, and then on V and on A, and maybe as like a whole vector of these things. Okay, so if we were to call P on the first of these, how does this look? These need to be pattern objects. Okay, and then we can just map string here, and this should be pretty good. Okay. All right, so now we have position, velocity, and acceleration, and then some kind of step for something with position, velocity, and acceleration is what? Increase the velocity by the acceleration, increase the position by the velocity. Are updated in the following order. Okay, so what do we need to, so maybe we can decompose these, px, py, pz, vx, vy, vz, ax, ay, az, and add to px, or actually, here we go. So let's see, so it says it's doing these in order. So, so let's see. So we know that the acceleration, so the acceleration will change. Ax, ay, az. Okay. And so we do know how the velocity is going to change. Ax, BY, AY, EZ, AZ here. And then I think we can just do this to get around the fact that the velocity increases before the position does. All right. So now it's saying, okay, so we got a list of particles. All right. Map P to these things. And yeah, we could say maybe have like S on a group of particles here where we just map step to P, something like this. Okay. Here, here. All right, this is a function. And then here, and then can we do one step on this? Looks like we can. All right, and then so let's do something like maybe iterate on S starting here. Take maybe like drop a big number from this, and then something like map indexed, and then apply min key mdist, like here where the Manhattan distance on something like this is defined by adding the absolute value of px, dy, pc. Right. Okay, don't know how to create a sequence from map indexed. Oh yeah, so I have actually a function for this. Stack Overflow, it says. Map step to pp. All right, so it's not overflowing. It's not overflowing here. Don't think that it would have a problem with this. Okay. Yes. So this actually needs to. We'll just take the first of these after dropping this many. Okay, something like that. Another stack overflow. All right, let's see if this gives us an answer. Stack overflow. Map. Oh, I see. It should just iterate. No, this should be fine. Step. Okay. Don't see a problem yet. This gives us an answer. Okay. Yeah, there's the Stack Overflow. I guess maybe drop is not the right. Maybe drop's not the right way. Take and the last here. Okay. Stack. All right. Well. Anyway, let's just take this down and see what this gives for an answer. So it says 457. Still says 457. So let's try it. Shoot. Typed it in wrong. Okay. Well, we can keep an eye on things here while we wait. Okay, so this does seem like eventually it does sort of reach this point where 457 becomes the guy. Too recently, got to wait 35 seconds. And yeah, this also might not be the right answer. just because I might have to like do more steps here. But we'll see. Okay, that is the right answer. Rank 68. Turn to day 20. All right. Okay, so saying collisions, particles collide if they ever exactly match. Because particles are updated simultaneously, more than two particles can collide at the same time. All right. Particles are simultaneously destroyed. On the next tick, how many particles are left after all collisions are resolved? Great question. Okay, so we maybe want to say something like, if we have a collection of things here, we can group by the thing and group by first. And then like a filter, here we go. We'll say for KV in group by first when count of V is 1, and then for KK like this here. Okay, so now what we want to iterate on is, I think we can just comp S. I think we can apply these in any order, but I think remove collider should be done first. Okay, so now let's just get, I guess, the first one of these things. Okay, nth not supported on long. All right, so group by first and call. Remove colliders from something where we got like 1, 2, 1, 3, 2, 3, like this. Don't know how to create a sequence from a long, okay. Group by first. For KK and K, I see. Right, the K actually doesn't matter at all. Yeah, because that's just the position here. Okay, good. Okay, null pointer, huh? So interesting. Yeah. Okay, so let's see. I don't see a problem yet. If we just try, can we just apply this to this here? No, we can't. Well, this shouldn't be too much of a problem. The only thing I can think is, nope, not sure yet. Okay, so here, let's call remove colliders on this part. Okay. Okay. What's the first of these? All right, and then what's the first of these? Okay, looks like I'm wrapping it in too many collections here, but I don't understand why yet. So the first element of these, okay, and then what's the first of this? It should be the position, correct. But now it's saying, what if I just take one here? Same problem? Yeah, it's the same problem. When the count of V is this, then, shoot, there, that's it. Okay, all right. Okay, once we get rid of this code, run this will produce an answer. I kind of want to count here. 448. What is 1,000? Still 448. Good enough for me. Good answer. Rank 34. Nice, nice. Was glad to have gotten some. Was glad to have gotten some points this time. Let's talk about the problem a little bit. Yeah, I'm surprised that people were having trouble. I certainly made some mistakes. So yeah, basically what this is a state transition problem. Seems pretty straightforward, where the inputs are a 1,000 particles that are all expressed by their position, velocity, and acceleration. So basically at each step along the way, the particles are going to have their velocities updated by their accelerations, and then they're going to have their positions updated by their velocities. So in my step function, reason that I'm adding position to velocity to acceleration is just because I need to, the way the rules are laid out, it says that you have to increase velocity first. So if I were doing this in like a more readable way, then I would have like maybe something like Vx, like VDX, to represent the new velocity here, and then just use like symbol substitution to make clear what I was doing, but this was just a little bit faster to write. So this was straightforward, and then I defined like sort of this step driver function here, which is just, okay, you have a collection of points. I just want to run step on every single one of these. And then, yeah, once I have that, I can basically just do things this way. Here we go. Okay, so yeah, I guess I can talk about my solver here. Oh yeah, my parse function was pretty straightforward. So actually, let's unroll this a little bit. So yeah, so first of all, call slurp on the input, and then I have this SM for smart parse, and which just basically it has lots of like little behaviors for these kinds of problems, but basically if something has new lines in it, it breaks it up by new lines, and if a line has spaces in it, then it breaks it up by the spaces. So that was all I needed here. So then this gave me basically a bunch of a sequence of a list of lists of words. Each word was position, velocity, and acceleration. So I luckily wrote a correct regex parser for these, for each of these. So then I was just representing these as, I ended up representing them as a vector. That seems, I bet that doesn't matter. We probably just represent them as lists. Should be fine. But for these problems, it's kind of useful. And then, yeah, basically what I did once I had that is I called iterate on, well, just S to start here. And then for some reason I kept hitting Stack Overflow that I didn't understand. So I'm still not sure what's going on here, because the way that I understand iterate is that if I'm calling something like drop, it should be just getting rid of all of those intermediate results. The head there should not be retained. But I guess that isn't the case for whatever reason. So anyway, so I did this I think I ended up doing it like 5,000 times or something. And this function here just basically takes a list of things and then indexes that with a number. And then so what this final function does here is this says, basically given a comparison function mdist, which takes the Manhattan distance to the origin, which one of them is closest. So if you watch it over time, you can see that because some particles are like crossing the origin at different times, in the early days it's pretty chaotic. But then as you get more and more iterations in, and eventually it settles on this one answer, this 457 here. And yeah, I think basically the reason for it is that it just has so there are probably a few different particles with a small acceleration value like this, and then it just happens to be that this is the one that sort of goes closest to the origin. And then yeah, for some reason I'm just misinterpreting the way iterate works here. So yeah, I guess I'm glad I didn't have to do more than 1,000 iterations. Yeah, at first I entered my puzzle answer in wrong, which was unlucky, but was still able to get some points. And then in part 2, the remaining sort of snag that they gave you is that particles can be destroyed when they share a position. So this turns out to be something that Clojure is good at solving. So I wrote this remove colliders function, and what this does is it takes a collection of things and then uses the group by function here. So what this says is that your collection is going to have it's a list of sequences of things. The first thing in the sequence, which in our case is the position, is the thing that we care about. So we're basically going to group every particle by its position. And then what this does is this says we're only going to consider the case when the particle is in a group by itself. And then when we do that, we're going to just emit. So this is just a list comprehension on roll right here. So we're just going to emit that particle. So so yeah, our iterate function changes to just we want to remove colliders before we call S here. And then instead of finding any kind of particular value in there, we just have to do a count. And after 1,000 steps, we get our answer here. And if you bump this up to 2,000 steps, then the answer is the same. And that was good enough for me. So yeah, so that was it. So pretty fun problem. Take a look at how far away from the leaderboard I am. Looks like I need about 600 probably by the end of this. I'll probably need around 700 points to get up there, and I've got 448. So 5 days left. So I would say a stretch, but perhaps in reach. So this was fun. Glad to be in the top 100 for a day. And that's all I've got. I'll be doing this tomorrow. Thanks for watching.